Today, we want to review the basics of solving equations by reading the expression and doing inverse operations in reverse order. This is the game that we're playing this week. Solving equations by doing inverse operations in reverse order. This is going to lead us to understanding how inverse functions work. And we're going to start by looking at functions as just combinations of operations. The equations that we're going to be solving are going to have a particular form. There's going to be some function equals a constant. And by function, we mean just an expression involving the variable. And what's particular to this method is that we're going to have one instance of the variable. So the variable can appear many times in a function, but we care about some expression involving one instance of the variable. And equation is just asking a question. What do we need to plug into the x to get the constant? So let's remind ourselves about how function notation works and how simplifying expressions works. So I've got this nice simple function. F of x is 2x minus 5. So what we're doing is we're encoding the expression and we're giving the expression a name. We're just saying this is some function of the variable x. Remember to pronounce this symbol. We pronounce that by saying f of x. F is the name of the variable, and f is the name of the function. So f is the name of the function. And x is the variable that we use in the function. So the reason that we have this notation is it names the expression 2x minus 5 in this case. It names the expression, and it also includes a space for the input. So f of x is 2x minus 5. F of whatever's in the parentheses, that's what we replace with the x. We replace the x with. So if we want to evaluate the function at a particular value of x, we could say find f of, and then we plug a number in, f of, let's say, 3, that'll do. So what this means is that we're going to replace the x in the expression with a 3. So this says replace the x in the function f with a 3 and simplify. So for our function, f of blank is 2 times blank minus 5. So f of 3 is 2 times 3 minus 5. I just replaced the x with a 3, and then we simplify the expression. 2 times 3 is 6. 6 minus 5 is 1. So we would say that f of 3 is equal to 1. And this keeps both pieces of information in one statement. This keeps both pieces of information in one statement. That's the benefit of using function notation. And just saying y is 1 when x is 3, f of 3 is 1 includes the input information and the output information in one statement. So it includes the input 3 and the output 1 in one statement. When we start thinking about graphs, it's like another way of keeping track of an ordered pair. X is 3, y is 1. So it works like an ordered pair where x is 3 and y is 1. It keeps both pieces of information that are related through this function together. Function notation is useful because instead of just an ordered pair, a generic point 3, 1, it's saying how 3 and 1 are related. F of 3 is equal to 1. If we put 3 into the function f, then we will get 1 as an output. And this just works for, this is for this function. I could say find some other values. Say find f, oops, it's lowercase f. Math is case sensitive. Got to watch out for that. So if I said in a different problem, find f of -4. That just means we're going to replace the x with the -4 and then simplify. So I write the expression. So f of -4 is going to be 2 times -4 minus 5. Really what we're doing is I just replace x with a blank set of parentheses, and then I fill in what I need to fill in. And then we simplify the expression. 2 times -4 is -8. -8 minus 5 is -13. So f of -4 is 13. This is how function notation works. It's just telling you to do some things to the x. If we change the variable, it would look the same. It's just a set of instructions. So if I write, it's lowercase f. If I say replace the x with a different variable, like I need another letter, like t. So if I have f of t, because I decided instead of calling my variable x, I wanted to call it t because it represents time or something like that. Then I just write, instead of the x, I just write t. So f of t is 2t minus 5. The variable is just standing for some quantity. The variable just stands for some quantity. So we notice in both cases, when I did f of 3 or f of -4, since f of x was 2x minus 5, I did the same two operations. We want to read what the function does. The function in this case multiplies by 2. First we multiply by 2, and then we subtract 5. In this case, the function is a set of instructions. It tells us what operations to perform on the x. The function is a list of operations to perform on x. The function is just a list of operations to perform on x, and our job is to read what those operations are and then perform those operations. The reason that we get to list off, just make a list of operations, is that we're only going to have one instance of the variable in the problems that we're working on this week. So for example, if I say that f of x is 2x minus 5, this is telling us to perform the operations. First, these operations. First, we multiply the x times 2, and second, we subtract 5. These are the operations that we've been performing. If I start off with a 3, then I do 3 times 2 is equal to 6, and then 6, I spelled 6 wrong. 6 minus 5 is equal to 1. So f of 3 is equal to 1. In the problem where I started off with a -4, I did -4 times 2 is -8, and -8 minus 5 is -13. The function is just giving me a set of instructions to follow. I opened up the box of the equation, and inside there were my IKEA instructions saying 1, multiply by 2, and 2, subtract 5. Although I guess I should have those weird IKEA outline people. So I don't know if I totally remember what they look like. Okay, so there we go. Now it's IKEA instructions. So these are not things that we're writing down. So a lot of times when we're in math class, we see the teacher write some stuff down, but the teacher is writing some stuff down while they are talking. This is stuff that's just going on in our mind. This is not something that we are definitely writing down. I'm not saying here is how you write, here's what you write down when you're solving equations for me. This is just stuff that's going on in your mind when you see this expression. So when you see this expression, 2x minus 5, this is what it looks like when you're looking at a thing. This is IKEA's way of looking at a thing. And saying, this is just what you're thinking in your mind. When you see that, you think this. So I'm going to go comic book style and make a little thought bubble. So this is not something that you're writing down. This is just something that when you see this expression, this is what you're thinking of. This is what that expression is telling you to do. Multiply by 2 and subtract 5. This is because multiplication goes before addition unless there are parentheses. That's the other thing that's going on here. We are also thinking about all of our rules, and we're thinking that multiplication before addition unless parentheses. So we're also thinking that. I'm trying to make poofy parentheses a thing where you're just thinking instead of like parentheses and then you have the square ones and then you have the curly ones. I think poofy ones should be just stuff that you're thinking about. Also because I didn't want to like write the whole thought bubble all the way down the bottom here and all the way across the top. So I guess I'm just being lazy, which is on brand for me. So we see this expression 2x minus 5 and we're thinking we multiply by 2 and we subtract 5 because multiplication goes before addition unless parentheses. Always remember, we got to call back to our operations that we've been talking about this whole semester. Everything comes back to addition, multiplication, and exponents and how we think about those operations. We've just been adding to that ever since. All right. So if I write a different equation, a different expression, let's say g of x, just to do a nice proper callback, if I write 2 parentheses x minus 5 close parentheses, now we will be thinking of a different set of instructions. We know multiplication goes before addition unless parentheses. So there are parentheses here. So now when we see this expression, we think first we're going to subtract 5 because the parentheses say to do that first, and second we'll multiply by 2. So now this is what's going on in our mind. So if we're going to plug into this function, we'll first subtract the 5 and then multiply by 2. This is going to give us different results than we had before because it's a different function. So here we are over here on the side. And then we see this expression and we think this. I don't know why the thought is coming out of his nose, but there it is. Because we're still thinking multiplication before addition unless parentheses, and there are in fact parentheses in this one. So if we plug in values of x, we're going to get different quantities. If I try to find g of 3, it's going to be 2 times 3 minus 5. not 2 times 3 minus 5. It's 2 times 3 minus 5. It comes across really terrible in English, which is why we write things down in math. But if I wanted to evaluate this expression at this function at 3, first I would do the 3 times 5, sorry, 3 minus 5, which is negative 2, and 2 minus 2 times negative 2 is negative 4. So in this case, g of 3 is negative 4. Different value because it was a different function. On the other hand, notice that we have 2 times x minus 5. We have multiplication and addition, and there's parentheses. We also know that multiplication distributes over addition. So we could rewrite our function using that. So we also might notice, hey, multiplication distributes over addition. We also might notice that multiplication distributes over addition. And so we can rewrite 2 times x minus 5. If we distribute the 2, I can write an equivalent function, 2x minus 10. So here is another form of g of x, 2x minus 10. If it's the same, then we should always get the same thing when we evaluate it. G of 3 is going to be 2 times 3 minus 10. So let's plug in the 3 into this form. 2 times 3 is 6. 6 minus 10 is still negative 4. That's good. If we got a different value, then all of a sudden these are not the same function. So we might be thinking, we might notice this. Someone else will come along and say, hey, they're thinking multiplication distributes over addition. Or they might even say it out loud. Now, I put a thought bubble, too late for that. So they're thinking multiplication distributes over addition. So they rewrote the function as 2x minus 10, and it was the same thing. When we see 2x minus 10, if we wanted to write this down is operations. First, we're multiplying by 2. Since we've removed the parentheses, now the multiplication by 2 comes first, but instead of subtracting 5, we are subtracting 10. And all of this is happening by while we're naming the expression. We're just giving the expression a name. Expressions and functions usually get like one-letter names, like f and g and h. It gets really messy if we start. I will call this function Robert. So they're like, oh, Robert of x. And it sounded very formal. But then they kept having to write Robert of x equals, and then let's just give them one-letter names, which is totally the strategy I would employ if I had kids, like human kids. A, here's my second child, B, here's my third child, C. Much simpler. All right. So in the context of equations, we want to look at what's happening. That is correct. There are several reasons why I shouldn't have kids, and that's naming them with one letter is pretty low on the list. Fortunately for any kids that I would have, there would be another person involved in the having of the kids, and they would have veto power over the naming of the kids. See, like I know George Foreman named all of his kids George, I don't know how he got away with that. George Foreman must be a really cool dude because he's like, well, I'm gonna name all my kids George, and he didn't do that alone. Someone's like, oh yeah, that sounds dope. Let's do that, George. Let's name all of our kids George. So I kind of wonder, or maybe George thought he was just being funny. He's like, well, I'm gonna name all my kids George, and then they're like, oh, all right. He's like, well, wait, I was just, well, all right then. I think I think one of the things that I think we should do is that we give the kids names, but I think at a certain point the kids should be able to decide what their own name is, and then we all have to change it. So like, because they can't really do it when they're just babies, because babies are really kind of useless, right? They're super cute. That's their big thing. But I'm like, oh, hey baby, what do you want to call yourself? And the baby's like, I can't even understand language. So you're like, all right, we're gonna name the baby George. This baby's gonna be named George. But then when the baby grows up and starts having ideas about names, like when it's a teenager, it's like, oh, I don't want to be George anymore. I want to come up with a new name. I think they should go through a time where they try out different names that they like, or they could just stick with George. They're like, oh, I'm fine with George. But as teenagers, you shouldn't let them make big decisions like about what they're going to be called as adults. But at a certain point, they're like, oh, you know what? I'm not going to be George anymore. I'm going to be, I don't know, Colson, for whatever reasons. Let them have their own reasons for coming up with a name. And then we should all just agree to that. And it's like, all right, you're Colson now. I had to come up with a name, and my dog is just sitting at my feet. So yeah, so you start with a default name, like a child's name, because you're not capable of coming up with one on your own. But I think by the time we declare you an adult, I think it's time to pick your own name. So you've been thinking about it for a few years. Start thinking about it when you become a teenager, and then when you age into adulthood, which is arbitrarily set at 18, maybe we can all get together. Say, hey, what are you going to call yourself? And it could be just like, oh, I'm going to go with the default. I thought George is awesome. I've been enjoying George. I've tried on a couple of different things, and I'm just going to stick with George. And everybody's like, oh, yay, George. And then we have, like pizza and cake. Or the kid's like, oh, nope, my new name is Bob. I will now forever be known as Bob. And everybody's going, yay, Bob. And then we bring out a cake and pizza, and there's no name on the cake because we didn't know what the kid was going to pick. Or maybe they decorate the cake, and that's how we find out. I don't know. I'm just, yeah, kid wants to be Spider. And I'm sure some parents like, oh, people are going to think strange things about you if you call yourself Spider. And the kid's like, oh, no, legally, I am going to be Spider. And then all we have to do as a society is stop throwing negative connotations on someone picking their own name because it's different than what we expect. Because right now people would say, oh, there's never going to be like a President Spider Jones. It's like, oh, well, there would be if we just get over the fact that it's just a name. And it's even better because it's a name that he chose, not his parents. You know what I mean? Anyway, what were we talking about? Oh, that's right. Naming functions. Functions always have boring one letter names. But functions are not sentient beings, so it's okay that we just assign them names and they just accept it. Maybe this is going to all come back to haunt me when the functions gain sentience and take their revenge on me for giving them these boring one letter names, but it wasn't my fault. I didn't do that. Anyway, I'm glad all that got recorded. See, it's okay that this weird stuff gets recorded and that I make mistakes all the time because it's like there are like 5 people that are watching the videos. So it doesn't matter that they're up on YouTube. It's like, oh, it's up on YouTube. It's going to be there forever. Okay, first of all, no, it's not. I'll take them down eventually. And second of all, it's not like people are going to see these. What is like Leach's math gonna go viral. It's just not. So anyway, I started the YouTube channel because I ran out of space on Canvas for storing videos. And then for a long time, I also sold a guitar amplifier. And for a long time, my most watched video, even though I had over 100 students, my most watched video was just people checking out my amp because they were considering buying it. And that was, so my most popular video was like 230 videos were two like 30-second clips just demonstrating that everything on the amp works, even though it was very old. Anyway, so the way that the function stuff works in an equation is that we'll take the function and I'll say solve. Once I use the word solve, I will always be giving you an equation afterwards. So a lot of times, solve is used for do a math problem. I specifically use solve in equation context only. So when we simplify 2 times the difference of 3 and between 3 and 5, I didn't say solve this expression. To me, that doesn't make any sense. If someone says solve this expression, I think they sound weird. If you say to me, solve this expression, you just ask me to pilot a car or drive a plane. It sounds weird to me. It gets the point across, but it just sounds weird. And I think there's something wrong with you. I don't think you have enough math experience to be using these math words. That's just me though. I mean, no one really cares except me. I'm the weirdo here. At least I accept that. So if I'm going to say solve, I'm going to say solve f of x is equal to, pick one. What did I use before? Oh, I did 2x minus 5. So f of x equals 1. And this is with previously where f of x is the 2x minus 5. So I'm asking the question, what do we put in for the x to come up with 1? What x will become 1 after we multiply by 2 and subtract 5? So we're solving the equation 2x minus 5 is equal to 1. The 1's outside here, it's an output. I'm trying to figure out what the input is. So I'm trying to find out what goes in the parentheses to make the output 1. I know I always pick with equations that we're familiar with already. And I predict that you would all add 5 and then divide the result by 2. And that's exactly what I want you to do. But I want this extra stuff to go along with it. I want you to read the expression, and I want you to see this expression here. And I want this expression to make you think, okay, I'm first going to multiply by 2, and second, I'm going to subtract 5. And that turns an x into a 1. This is not what you're writing down. This is just stuff that you're thinking. I don't know why you're standing so far away and thinking it, but that's okay. Because then you can come up with a plan for undoing what happened. We solve by performing inverse operations in reverse order. So we want to turn a 1 back into an x. So first, we're going to undo the subtracting of 5. So we add 5. And second, we undo multiply by 2 with divide by 2. So I'm going to take, this is my plan for solving. This is becoming a thing now, I guess. I'm just drawing little people thinking of these things. But I want to emphasize that this is not something that you necessarily have to write down. If you can't remember how to do it without writing it down, then go ahead and write it down. But it's not something that I'm going to force you to write down, because I think it's really weird when teachers are like, "I'll do it this way and write it down this way." I think that's just weird. I mean, they don't understand how your human mind works. I don't even understand how my human mind works. I know the things that it does. I recognize certain behaviors that it has, but how it actually functions, weird. Who knows? And these, I'm just going to take one and I'm going to do these things to it. I'm going to start off, I'm going to say, well, if I'm going to end up with 1, I need to add 5, and that's going to get me to a 6. And then I need to take the 6 and then divide by 2, and that means I must have started off at 3. And that makes sense. If I go back and plug it into here for the x, if I take a 3 on this side, 3 times 2 is 6. 6 minus 5 is 1. 1 plus 5 is 6. 6 divided by 2 is 3. That's the connection between the 3 and the 1. When we write f of 3 is equal to 1, we're saying f of 3, oops, that means 2 times 3 is 6. 6 minus 5 is 1. So going backwards, 1 plus 5 is 6, divided by 2 is 3. This is the way I want us to read equations. So if I pick a different equation, I'm going to leave off the function notation because that was just extra stuff. But let's suppose I have a different equation. I have 2 times an x minus 5. Then the x minus 5 is to the 3rd power. And let's say that is equal to 18. 18 is good. So this function or this expression, I didn't name it as a function, so I should just call it an expression. An expression is like an unnamed function. So this expression says do some stuff to x, and the equation says after you do that stuff, you'll end up with 18. Where did you start? So we identify what happened to the x. This is the reading exercise that we had before. And we take the x, and the first thing that happens is we subtract 5. And the second thing that happens, we've got multiplication and exponents. And exponents go before multiplication. So we next do the 3rd power. And third, we multiply by 2. So there's a lot going on in just coming up with this shorthand. We have to read what's happening in the expression. First, we subtract 5. Then we do an exponent. And then we multiply by 2. The reason that this happens is that we're thinking exponents before multiplication, unless parentheses. Remember, unless parentheses not just means there's parentheses somewhere in the expression, there's parentheses that tell you to do the multiplication first. So we did this subtraction because there's the parentheses said to do this subtraction first. And then there's an exponent and multiplication. So we take the x minus 5 to the 3rd power. Then we multiply the result by 2. If I wanted it the other way around, I'd have to put parentheses around the 2 and after and before the exponent. So here's how we turn an x into an 18 in this equation. X has turned into an 18 by the end of this process. So to undo this process, our plan for undoing it, to turn an 18 back into an x, first, we divide by 2. Second, we do a 1/3 power, because the inverse of our exponent is a reciprocal exponent. And third, we add 5. So I'll start off with 18 and divide by 2, and that's 9. And then I'll do 9 to the 1/3 power, which I'll need a calculator for, because I don't know the cube root of 9 off the top of my head. So I'll just do 9 to the 1/3 power, 2.080083823. That goes on too long. Remember, this is not stuff we're writing down. This is stuff that's happening on our calculator. And then we'll take the 2.080 and add 5. and get 7.080. So this process is not happening on paper. We're just doing 18 divided by 2 is 9. 9 to the 1/3 power is 2.808. And then 2.08 plus 5 is 7.08008. 382. So this is what's happening. This is all happening in our mind. We read the expression, we come up with our plan for solving. The plan for solving happens on our calculating machine. And then on the paper, you just look at the equation and you're just like, oh, this just means x equals 7.080. So this all here is mind stuff. This is calculator stuff. This is what goes on the paper. Any questions? So I wanted to review today the function notation, because sometimes I ask you to solve equations by defining a function and say, solve the equation f of x equals constant. But I want you to do the same thing. I want this to happen in your mind. And if you need to write this down, then that's okay. I usually write things like show your calculations. What is it that you need to write down? Go ahead and write that down. That kind of gets pushed aside because there's the paper that you're writing on, and then there's the typing. That's how you're reporting your answers to me. So really, if I do this quiz, when we do this quiz, I have to do it too. When we do this quiz, all that's going to be written there is the 7.080, and I'm going to say yes or no. Because if I can write down, if you could look at the equation, I want you to get to the point where you can read the equation and know what happens next. We're going to start off. I'm going to ask you to write you should write everything down. But the goal is to not have to write anything down. Just look at the equation, say 18. First, I'll divide by the 2. Then I will raise to the 1/3 power. And then I'll add the 5. And then I'll check by taking the 7 point, and I'll check by subtracting 5 and then raising to the 3rd power and then multiplying by 2. Now you know that that 7.08 is correct because you checked your answer. Any questions? So that way, if I mark something incorrect, because you checked your answer, if I mark something incorrect, it comes down to you failing to read the expression correctly, or maybe just punching the wrong buttons on your calculating machine. Either way, you go back and do it again, put in the right answer, and then I give you the points. Any questions? Comments? Snide remarks? All right, that's going to do it for today. I will see you all on tomorrow. Have a great day, and thanks for playing.